Guys do what you should do when you're studying for this stuff, and the first thing you should do is kind of make a list of the important topics, the important things you're supposed to understand. So let's see. 3.7 was what I called kinematics, the equations of motion. One little thing there is don't forget the units. So if you see me put dot, dot, dot after your number answer, there should be some units there, right? So you only lost like a point, I think. This thing's going to drive me crazy. But there's really nothing to put here. It's just the S, V, A stuff, right? That's what I really focused on in that section. You guys with me a little bit? A little tiny bit? Some of you just used the wrong function at the right time, or the right function at the wrong time. There's some incorrect thing going on. Can't like it. So for example, if I say something like, when does the particle turn around? Which one of these does that focus on? Yeah, I like the second one, or V. I don't know which one you're doing. Okay, I like it. That's the velocity. I love it. Okay, maybe. So that's 3.7. 3.10 was the linear approximation stuff, which, if you just call it what it is, that's all it is. The one little thing you've got to be careful about that actually happened to you on this quiz. On the practice exam, there's a function, I think it's this guy, right? The very first problem? Yeah. So if I want to create the linear approximation, I just find the tangent line at a equal -2. I find the tangent line. And that's algebra, really, with a little bit of calculus. Take a derivative, get the slope, get the point, plug it into the equation of a line. That's algebra. I like it. But if I ask you, approximate this, am I going to put this value in to my equation? No. If I want to approximate 1.03, what does x have to be to make this 1.03? So if I create a linear approximation to this, if I find the tangent line to this, and then I want to use it to approximate this value, x isn't 1.03. That doesn't make any damn sense. I get 4.03. I'm not going to get the right answer. What's x? Yeah. Well, 1.03 minus 3, yeah. Negative 1.97. That's what you guys see what I'm saying? If I'm creating a tangent line, creating a linear approximation for a function where the inside isn't just x, then I got to be careful about how I make this value happen. All right. That's the only little thing about that section you've got to be careful about is what is the value of x I'm trying to use? Well, the function is x plus 3, and I want to have 1.03. I've got to figure out what is x to make that happen. That's the value that I use. Well, let's do this problem. Okay. I know I got on the answer to you. Who cares? So how do I create the tangent line equation? I need two things. What do I need for the equation of any line? What do I need? Slope and 1 point, right? Because if I didn't know calculus, I might need 2 points to figure out the slope, but we know calculus, right? So how do I get the slope? How do I get that? Derivative. I love it. All right, kick ass. So then, what's the derivative of this? Yeah, and I want the slope at what point? At what value? I want the slope at. All right, so what's f prime of negative 2? One. I like it. So he's motioning to me in the back. You guys are, I mean, nothing has changed from algebra. Not a damn thing. We just know a little more. So find the equation of the line that. What do you always need for that? Slope and a point. We just have more ways that we can find slopes now. That's all. That problem hasn't changed. So we get the slope. What's the point? And there is one. I like it. Change the Roman numerals there. What's the point? Negative 2, comma. What do you get when you plug a negative 2 in here? You get the natural log of 1, which is 0. And now you just put all that together. Now, and again, you've got to get over getting stuck in stupid little details. The book calls the linear approximation f of a plus f prime of a times x minus a. All right, that's bullshit, really. Y minus y1 equals m times x minus x1. Call m f prime, because that's what it is. Give it a instead of x1, ooh, and f of a is y1. It's the same stupid thing. That's why linear approximation is tangent line. That's why. This makes it look, oh, it's all brand new. No, it's also old shit. All old shit. So now I just put the stuff in there. So I get y minus 0 equals m times x minus negative 2. So plus 2. So y is x plus 2.
You don't want us to use that LX equation, L of X.
So the point is, this is this. You want to use this? Great. You want to use this? Great. Why are they both great? Because they're both the same thing. They are both the same. What is m? F prime of a. Let me call x1 a instead. What do I get when I plug a into f? I get the y value. They're the same equation, which is why I say when they ask you to find the linear approximation, you can translate that into find the tangent line. Yes?
Then how does the, like on the test or on the quiz, it said then use your approximation to evaluate.
Yeah. Okay, you ready? Let's keep going with this, and then it'll be related to what you got to do for the corrections. Let's see. So there we got this equation. And what did we say x had to be for this to be true? What's the value of x I'm going to use? So what does this really, really mean? Let's get this all put together. That's the tangent line to this function at that point. So close to that point, this function follows this line. They have the same or very close outputs. So whatever value I would normally plug into this, I can get an approximation by instead plugging it into this. Maybe.
Plugging what in? Negative 2?
Let me say that again. Whatever value I would normally plug into this, I can instead plug that value in here to get an approximation. So if I want the natural log of 1.03, that means I'm actually plugging negative 1.97. That's this, right? Is that cool? Why did I write like that? So I can identify what x is. What's the actual input that I want for that function? If I want to figure out what the natural log of 1.03 is, what does this function need input into it? Negative 1.97. How do you make a 1.03 show up in here? All right, that's easy. What's x plus 3 equal 1.03? Negative 1.97. So if I have this, square root of x plus 1, and I want to know what the square root of 4 is, what would you put in here? 3. All right, no big deal. So if I want to know what the natural log of 1.03 is, but the thing I'm using is natural log of x plus 3, take a second to figure out what x is to make what you want to have show up, show up. So the input I'm actually using is negative 1.97. And now put it in there. So I can either, so what this whole thing is saying is if I put negative 1.97 in here, in my calculator, won't I get this? I'll get a value for this. Are you with me? Yes? Yes? But we just figured out a much simpler function that I don't even need the calculator to use that should be a decent approximation to that. So if I, instead of putting negative 1.97 in here and having to use my calculator because I don't have natural logs memorized, I could put negative 1.97 in here. Will it be exactly right? No. Is negative 1.97 very far away from negative 2? So it should be a decent approximation because at negative 2 is perfect. Let's check it. At negative 2, what do I get here if I put a negative 2 in? You get? What do you get when you put a negative 2 in? 0. And what do you get when you put a negative 2 in here? Natural log of 1, which is 0. So at that point, they perfectly agree. As long as you don't go very far away from this point, your output should be close to the outputs of this, using this instead. So if you do natural log of 1.03 in your calculator, what do you get? I like it, right? Right? Cool. And what do you get? So that's the exact answer. I put the dots there, so that's the exact answer. I just didn't feel like writing it all out, but there it is. There's the exact answer. That's if I use this, and I have to use a freaking calculator because I don't know what the hell LN is. But this, I don't need a calculator for this. If I put a negative 1.97 in here, I should get a decent approximation to what the actual value is because I didn't go very far away from negative 2. So what do I get when I put a negative 1.97 in here? What do you get? What's 2 minus 1.97? Don't be plugging that in the calculator. 0.03. Would you say that those are pretty good? Close. Oh shit, yeah. Right? I like it. So I have a function that achieves an outcome for a certain input. I can create a function that's much, much easier, a linear function, that as long as I don't go too far away from the value I used to create it, should come up with very good approximations to what the actual value is. Every differentiable function has a linear approximation. Now, natural log looks like this. So its linear approximation is going to be really good. It's really nice. If I have a function that is going insane, I can't go very far at all away from the point I used. Because we already knew before that if I go very far away from a crazy function, the slope is changing like crazy. So therefore, any linear approximation wouldn't hold if I went too far away. Okay. You want to do another example? Yes?
Can you continue the question versus find the general of x value? Does that make it?
Where are we at, sir?
Same question.
Yeah.
The second part is find the general of x value. Does that make the approximation correct?
Oh, okay. Let's do that. So that was this process here. So I know that my linear approximation is x plus 2. And I want, where'd it go? So I want to be within 0.01 of the right output. So I want x plus 2 minus 0.01 and x plus 2 plus 0.01. I want to be off by 0.01 from this guy. I don't know if you guys remember, we did this before. I said the ceiling and the floor. We did this. Let me put it up on the overhead. So is that cool? Isn't this within 0.01 of the correct value? That's how you write. Within 0.01 would be 0.01 down and 0.01 up. So I want the output values to be within 0.01 of the correct value. Now this is that next level where, depending on what you're going to use the estimation for, if you're going to use the estimation to construct some crazy thing that has to be balanced or else people are going to die, you probably want to make your tolerance really, really small. Right? You don't want to be off by much at all. But if you're just, and it depends on what the function itself is doing, what the original function, how weird that sucker is. Right? That's what's going to come out in this. So let's see what this thing looks like. Are you on? Let me just use my calculator. Turn you back on. Let him warm up. Okay. So some of you guys might remember doing this. So if I put in here, you put my floor is x plus 2 minus 0.01. Then I'll put the thing I'm trying to capture, the natural log of x plus 3. And then I'm going to put the ceiling. So what I'm going to get is, here's like the ln function's been shifted over. And then I'm going to have these lines that come in, and I'm going to try to find out, where does this sucker stay in there? I don't want the difference between my lines and the actual function value to be more than that. I need it to stay in this region. Then I'm going to be within 0.01. So see what this thing looks like. Let me zoom 6 just to make sure there's no freaky window. We're probably going to have to zoom in. There's the ceiling. There's the function. Oh yeah, I went the wrong way. And then there's the floor. So I definitely want to zoom in. Can you guys see the region I want to zoom into? I want to zoom in right there. So let me put a zoom box around that sucker. Let me stop right here. Does this feel familiar? We did this a couple times before, but it's been a while. So zoom box. This is the zoom enhance from CSI, except this one's not bullshit. We zoom in. And it shouldn't be surprising we're zooming in around a equal -2. That's where everything interesting is happening. It was the floor and then the ceiling. And now I want to zoom in some more. So I just do the exact same thing. Zoom, box. I'll come over here just to be careful. Let me do it right here. Let me see if I can still see everything. So there's the function. Yeah, see now we can almost, do you see how we're getting close enough to see something happening? I can now see the separation. I can see where my function enters the region and where it leaves the region. That's the points I've got to use. I need to live within those points. Let me zoom in one more time. I can see where it enters down here. See that? I can see where my function enters. Right there. This is bad. And now this starts to be good around here somewhere. And then it starts to be bad again over there. I probably could have done it off of this, but I'm going to zoom in one more time. Jihad. Okay, that should be plenty good. There's the floor. There's the function, that's where it comes in, and that's where it goes out. And there's the ceiling. So the ceiling isn't the problem here, right? It doesn't even come close to the ceiling, but between what two x values do my inputs of the actual function live within the error that I'm allowed? I got to find this intersection and that intersection. And that'll be the two x values between which it's good. This kind of defines how far away from -2 I can get and still have an output that's within 0.01. So I just have to find those intersections. So to find this intersection, go to second calc, intersect, that's awesome. Make sure I'm on the right. So what I always do is, let's see, just got to be careful not to go on this one up here. I don't care about the ceiling, right? So enter, enter, enter. So there's the lower one, -2.135, roughly. And then just do the same thing for the upper one. And what was it we used? We used -1.97. That's why our estimation was definitely within 0.01. We didn't go all the way down to -2.13. Yes? You'd have to solve this equation. Yeah, so that's why we have to use technology to get this. I'd have to be. But I will say, use a calculator to find. Right? If I don't say that, don't use a calculator to do it for you. Right? That might be old school, but I believe in, students knowing how to do something instead of which button to push. This is a situation where I can't algebraically solve that. Not easy at all. All right, and then do the same thing for the upper bound, right? Second calc, intersect, yeah. Maria looks to be about right there. First curve, second curve, guess. So I can go up to -1.85 roughly. So if I live within there, if all my inputs are within -2 point whatever it was, and -1.85, my approximation will always be at most this far off. So again, that's kind of like related to what you're going to do with the output. You can make this smaller or make it bigger depending on how big of an error it would be to be far off or not so far off. People are going to die. You probably want to make this small. Okay. Do you want to do another linear approximation construction problem, or do you want to do something else? We can do another one of those, or? You guys are like, I want to be home in bed, sipping something, or sleep. Yes? Yes, okay. Let's see. Create the linear approximation to So what are the two things I need? What two things do I need for the equation of a tangent line, which is what we understand linear approximation to mean? What two things do I need? Slope, I love it. So how do I find the slope? Derivative. So what's the derivative of this dude going to be? I don't know if anybody at this point can realize, since the inside function is slope of 1, what's the derivative of 1 over x? What's the derivative of x to the negative 1? All right, let's just do it. Okay. So let's rewrite this. Is that cool? Yeah, just rewriting what the function is. What's the derivative? Sing it. Good. To the? Good. So hopefully somebody out there knows the derivative of 1 over x is negative 1 over x squared. Since the inside function really isn't different from x, it's just been shifted by 2, so it's still a slope of 1. There's not going to be any chain rule piece. It's just being negative 1 over the bottom squared. Okay. So what's the slope that I want? What do I put in there? What do I put in this? All of you guys. What value am I building this around? 3. Yeah. Well, I want it to happen at a equals 3. They have to tell me what value I am building this thing around. So if I put a 3 in, what do I get? Negative 1. So that's my slope. Check. And then the second thing I need is a point. Then the point I've got to use is f evaluated at what do I put into there? What's the only value I'm interested in for this problem? Okay. So what's f of 3? 1. Okay. All right, and now this is algebra now. I've got a slope, I've got a point. I can construct that tangent line, which is the linear approximation. Those two things are the same. So I try to point out, it's kind of evil, the book makes it feel like that whole section is brand new. I hate that. It's not, it's just the freaking tangent line. So what do I get? I get y minus what equals what times x minus what. I just got to throw stuff in the right place. So the point is 3, 1. Slope is negative 1. So somebody can yell out, put a negative 1 right there. Yeah. What goes here? 1. That's the y value. And what goes there? 3. Because that's the x value. So y equals negative x. Get out of there. Plus 3 plus 1. Is that cool if I just kind of get there quickly? Plus 3, and then you add 1 to solve for y. So that is this function simpler than this one. And don't even say in what way, Jeff. In every damn way, this function is simpler than that one. And this function will give very similar outputs that this one will, close to this input. So this would be part A, would be create the linear approximation. Part B would then say, use the linear approximation you just found to estimate Let's see. Let's say 1 over 1.1. So what does that mean x is? What does x have to be to make this what I'm looking at? We could do this. What does x have to be to make this what I'm looking at? 3-ish. How exactly do exactly 1.1? What minus 2 is 1.1? 0.1. Or if you really need to, how do I make x minus 2 become 1.1? I make x 3.1. Why is that a valid value to use? What did I build this linear approximation around? 3. And this is a decent function. It's not crazy. It's nice. So is 3.1 very far away from 3? No. So this means x is 3.1. So my approximation would say negative 3.1 plus 4. My approximation would say it looks to be 0.9. Somebody help me out. What is 1 divided by 1.1? 1 divided by 1.1. So this is the estimate. And the actual value, what are you guys getting? 0.90. 90, what is it?
90.
Oh, 9090, and it keeps going like that? I like it. So would you say that's a pretty good estimate? Hell yeah. And again, it really depends. A good answer would be, I don't know, Jeff, because, again, if you're off by this much and that means the whole thing topples over, then no, right? That's why you do that kind of thing over there, to see how far away you can be to use this estimate. But in general, that looks pretty damn good. I'd say that's really close, right? So when you tell me the exact value, don't round too much. You are trying to show how close your estimate is. Don't say, yeah, they're exactly the same. No, they're not exactly the same, right? Okay, maybe. Pretty damn close. Why again? Why are they so close? Because the value I used was not very far away from the place that they're exactly the same. So of course they're not going to be very far off at 3.1. Okay. I like it. So what do you guys want to look at next?
Are you taking questions from the quiz that you?
Oh, hell yeah. That's why you can give me.
I just have a question on number 2. It's the same thing with linear approximation, but just how would you approximate the definite portion of that part?
How would you do what, sir?
Like, how would you approximate the value at the end of it? Because the tangent line that I got was y equals 1 over 4. X
Yeah.
plus 1.
That sounds about right. So that's related to, so if your function you're working with, let me just make a different problem, was this, and I'm asking you to approximate the 5th root of 2.03, then what x value are you going to throw into your approximation? What x value are you going to throw in to make this actually happen? What would x be? 0.03. Do you guys see that? That's it. That's it. If I'm trying to approximate a value and I've got a function, I can see what the x has to be to make that happen. And then that's the x value I'm going to use. Not that big of a deal. It really, 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 really isn't. So that's one you don't need a calculator for. I purposefully gave you an x value that is divisible by 4 in your case, or divisible by 3 in other cases. So you don't even need a calculator to do it, which is the best way to be. Yes?
What is the difference between absolute extrema and relative extrema?
Can anybody answer that for me?
Is that local versus absolute?
Totally.
Okay.
So just like the book uses the word extrema in place of max and min, use relative in terms of local. Relative to what? Relative to the local. Okay, local max and min, same thing as relative max and min, same thing as relative extrema. Which one of those is easier problem to find, the local max and min, the relative extrema, or the absolute max and min? Which one is the easier problem? And you might think this is a subjective answer, but no. Which one is easier to do? What does absolute extrema involve doing? What do you have to do to figure out the absolute extrema for something? What's the first step? Yeah, take the derivative, right? Is that what you're saying? In order to find what? Critical number. Okay, first step really is find the critical numbers. Right? So say absolute extrema on A to B. Oh, I know you guys are going to love this. With critical numbers C, D, E. So then what I'm going to do is the second step is just going to be put A into the function, put B into the function, and then put the critical numbers that are in A to B. So say C is in there and D is in there, but E isn't in there. So then I have to do F of C, F of D, and then I just see who freaking wins. I just step back and see who's the biggest, who's the smallest. So absolute extrema is a much easier process. Now, depending on the function I give you, the problem itself might be gross because the derivative is weird or whatever, but still, the process is simpler. What does it take to find local extrema? First step is the same. First step is find the critical numbers. And what's the second step? I have to construct something. Sign diagram. And then the third step is to see, where's things positive, where's things negative, if it's going up and down. So there's definitely a few more steps. It's a little more conceptual. This is pure brute force. Find these, plug those shit in, and the ones out of these that are in there, just see who wins. Brute force. Conceptual. That's why this one is normally a little bit harder than this, but at this point, this shouldn't be that bad. Where's the only place where local max and mins can happen? At the critical numbers. Right. But not every critical number has to be a local max or min. We know this. Okay, maybe. You guys all right? So that's why we find all the critical numbers first, and then we investigate what's actually happening at those numbers. Or is there a max or min, or is it just a resting point? And of course, this whole thing is the same for second derivative. I like it. Which one? E. Ooh, I like it. Okay. So first thing with number 8, if I give you a problem, and Shannon, was that cool? Mm-hmm. Okay. If I give you a problem where I give you a position function and I start asking you questions like that, what's like the very first thing you're going to do? Just to get it done. Find the other two levels of stuff, right? Okay. Take the derivatives. What was it? Come here. Negative t cubed. It's 8t squared. And it's 0 to 8 for the time. So what's the velocity? I like it. And then the acceleration, I'll just do that. All right. So now you have those functions set up to reference when you need to. So the first several problems are stupid. You just throw the number in the right function. The first question that isn't like that is E. Train stops and heads back. Come an S. All right, this part, simple enough. How do you figure out when the train stops? Or it isn't moving, really, which is another way to say that. Yeah, figure out when the velocity is 0. So try to force this problem to make some sense. If I'm talking about a train heading somewhere, what should be true at time 0? That's when it is sitting at the station, right? People are getting on the train. It hasn't started yet. So sure enough, now, we're in calculus. You got to be okay with the answer not being whole numbers. But how do I solve this? Factor out a t. I like it. You can take a negative t or just a t. So you get negative 3t plus 16. So t is either 0 or t is, subtract 16 divided by negative 3, 16/3. I think these are hours, right? I can't remember. Yeah. And these are both multiplicity 1. They're both odd multiplicity, so the velocity does change sign. So at t equals 0, it's sitting at the station. It loads up with people and it heads out. Right? Then they realize, oh man, we forgot all the food for this turn at this time, so they have to head back. So this time the velocity does change sign. How the shit do I know that? I just said these are multiplicity 1. The velocity does change sign around those routes. So that is the time when it stops and heads back. You guys with me? So that's the answer to that question. But you do have to kind of make sure that this isn't just where they went, did we forget the food? No, okay. And then they keep going. Now I like part F. Part F will freak the shit out of people, but you just got to break part F down. Is this cool though, by itself? What's up?
Sorry, I didn't catch between we forget the food, let's ignore it, or let's go get it back. I just have to plug in 2 points before and after to make sure it's not opposite signs.
You can, or you can realize the multiplicity is odd, so we'll change signs around these numbers. Why does this one not matter? Because the other side doesn't exist for this problem. It starts at 0. So this is the possible time when it leaves. At this time, does it go back? Yes, the sign of the velocity changes. You could plug stuff in, but you shouldn't really have to.
The first one, t equals blank or blank, or t equals 16.
No, this is t equals 0. This isn't a blank.
Oh, it's hours.
Because if t is 0, this is 0, or if t is this is 0. Yeah.
I just meant, I think.
Oh, okay.
Hours was.
Hours, yeah.
Yeah.
Yeah. So this is the answer to that question. So this is not moving, but this one is, it's stopping, that's why it's not moving, and then headed back. Okay. And real quick, does 16/3 live in this interval? If it didn't, this would be a really weird problem. You couldn't even include that time. But yes, 16/3 is just a little over 5. I like it.
explain again how we know 0 isn't part of the answer?
So if the question would be, when is the train at rest?
Oh, okay.
That would have been part of the answer, because it is at rest here. But this question specifically is, when does it turn back? Which means it's been traveling for a while, and this is before it starts moving at all. So that's why that one is traveled this long, and then it turns back. But what about part F? Was that one all right? Part F of that problem? Yes. Yeah. Oh, yeah. I wasn't going to just go, okay. Part F has a few parts to it. What's the very first most important thing that you want to figure out in part F? No. So the question is how fast it's going. So the very last thing I'm going to do is use a velocity formula. But how fast it's going a half hour before, okay, I got to get time so I can plug it into that velocity formula. Half hour before it gets back to where it started. So what's the very first thing I should figure out? How do I get that, though? There's something else I have to do before that. Where the shit did it start, right? Now, this might be a simple question. I mean, you might look at the function and say, I can see where it started, Jeff. But what is S of 0? That's where it starts, right? That's where it starts. So what is S of 0? 0. I love it. So I made this problem make a lot of sense. It starts at the 0 position. Train hasn't left yet. It's 0 meters away from its home base. That makes beautiful sense. So that's where it started. How to figure out the time that it gets back to where it started? What's going to tell me it gets back to where it started? The position will be 0 again. So I need to take this and set it equal to 0. See, where else is that bad boy 0? When does it back? Something happens here that I'm not going to say happens all the time. It was very nice in this problem. So what's S of t? It's negative t cubed plus 8t squared. I could just divide by t squared because I already know 0 is an answer, but just in case you guys will freak out about that. Factor that bad boy. I get the t equals 0, I knew already. And I get t equals 8. So this one doesn't matter. That's when it started. So at 8 hours, just happens to be the end of this interval. I'm not always going to do that. You can't just say 8. No. At 8 hours is back to where it started because it's back to position 0. I like it.
So then would we do the same thing almost, but instead put 7.5?
Now I know that the time this problem is interested in is 7.5 hours. And what is it about 7.5 hours that I want to know? Velocity. So now I just have to do v of 7.5. Half an hour before it gets back to where it started, how fast is it going? And now it's just, throw that thing in there and see what it is. I like it. What will the units be on this? What will the units be? Miles per hour. I love it. Yes?
Should we worry about hyperbolic functions? Should we worry about hyperbolic functions?
Oh, hyperbolic. I mean, the most I would do to you is just ask you to evaluate like cosh of 0.7 or something.
Do you want us to do it by using the formula E to S?
Yeah, and if I ask you, I told you didn't have to really memorize anything from that section. So if I do ask you a question, I will give you the definitions. So I might ask you, verify that the derivative of this is this, and then I'll give you the definitions. It would be really, I know a lot of you guys think I'm evil. I'm not evil enough to ask you a question about something I didn't say you had to memorize and not give it to you. That would be, give me a few more years. Maybe I'll be that evil then. I said that same thing a few years ago, so I guess I'm not quite there yet. I mean, just a general point about that. You have to know that those hyperbolic functions exist. You have to know what they're kind of based on. But depending on where you go after this, you might never use them again. So if you're going to go to Calc 2, Calc 3, these will come back up again. So I want you to have some basis in knowing they're defined by exponentials. That's why the derivatives are so beautiful, all that kind of stuff. Right? So they're not like completely brand new to you in the middle of all this other shit. So I wanted to give you homework with it so you knew they existed, you knew kind of like how they worked. But I'm not going to make a big point of it right here, testing you on those. Okay. All right, let's do this. Let me interject. I didn't do number 7 on the answer key. Let's look at number 7. That's the one that comes right out of the book, right? So number 7 starts with number 45. I like 45. This is a beautiful example about why it would be impossible for me to do an example of every kind of problem you could see. That is